All right. Yes, ma'am. Yes. All right. So, piecewise, it's literally what it sounds like. It's pieces of different functions all on the same graph. But they're still considered functions because none of the x values repeat. All right. So even though they look a little funky, like they literally look like someone took different pieces of graphs, took a hatchet to them, and just sliced them and then spliced them together. All right. It looks like it. I like to call them the Frankenstein of graphs because that's what they look like. All right. Now, piecewise for a lot of students, they are. I don't necessarily think they're complicated to read, but if you look at them at first glance, they look pretty daunting, all right, because there's multiple functions in one. But once you learn how to read them, it's actually fairly straightforward. All right, in this class, I mainly care about can you read a piecewise graph and can you evaluate a piecewise function, all right, which we know all about evaluating. One of the easiest things to do in this class, all right. So, first off, like I said, the piecewise function is a function which more than one formula is used to define the output. So instead of it just being like x plus 3, it'll be, okay, x plus 3 for these set x values, then 2x plus 1 for these set x values, then 5x minus 4 for these set x values. All right. Each formula has its own domain. And the domain of the function is a union of all these smaller domains. Like I said, Frankenstein of functions. All right, they take individual pieces and they stitch them together. Now, this right here is how a piecewise function will look. You'll see f of x and then this little squiggle. Now, on the left side are your formulas. All right, those will typically look like how you normally see functions. So like x squared plus 3, absolute value of x minus 2, whatever. Next to those functions are the domains. So in other words, whatever domain is next to the function, that's the domain that applies to that function. Meaning that function's only applied for those specific x values. All right. So let's look at number 1. So this is what typically a piecewise looks like. And it looks ugly. Now, just to give you an idea of what it's going to look like, let me show you what this looks like in Desmos. And you don't need to do this, but just so you have a visual of what this is going to look like. So if you ever want to see a piecewise in Desmos, here's how you do it. You type in each function individually. So I have 5x minus 3. So y equals 5x minus 3. Then you do a squiggle bar, and you're going to type in the domain that's next to it. So x has to be less than 2. Now, what happened to the graph when I did that? What happened? It didn't move down. It just cut off. So it actually cuts off at x equals 2. All right. Now I'm going to continue adding on. So y equals x plus 8. I'm going to put my squiggles, and it's going to be from -2 less than or equal to x, which is less than or equal to 3. Oh, it has to be -2. All right. See what's happening now? I got another piece of the graph right here. All right. Then my last one. Y equals 1/3 x plus 7. And it's going to be when x is greater than 3. So let's just look at this graph for a second. Now do you see why I call this the Frankenstein of graphs? It's literally pieces of the graphs. All right? They don't necessarily connect either. Now, the one thing that Desmos doesn't do is give you the opened or closed circles. So just for reference, this would have an open circle because it was less than. Both ends of these would have closed circles because they're both less than or equal to. And then this one would have an open circle as well. All right, so that's typically what a piecewise graph looks like. All right. Now, here's why it's a little bit gross. Okay. Let's say that I wanted to evaluate, let's just look at the first problem. All right. Let's say I wanted to evaluate at f of 2. So f of 2, that's the same thing as what? Which value are we finding 2 for? We're finding where x is what? X is equal to 2. Now, if we go back and look at the graph, if we want x is equal to 2, all right, do you think I'm going to plug that into every single piece of this function? No. Why do you think so? Well, there's only one x equals 2, for one thing. But also, if you think about it, only one of these functions is going to contain x equals 2. Does anyone know which one they think will be? It's the first, the second, or the third? So take a guess. Where do you think x equals 2 is going to fall in here? Is it going to be with the black function, the red, or the blue? Well, let's see. So let's go back to my Desmos, and I'm going to actually type in x equals 2. Where does that straight line cross? Red. All right, so that means I'm using the second function. Now, if I go back and actually look at the original, why does it make sense that when x equals 2, we would plug it into the middle function? If x is equal to 2, why would we plug it into the middle function? Well, it's where it landed on the graph, but what about the function would tell us that's where it would land without looking at the graph? Right, so if you plug 2 in for the domain, is it true that 2 is between -2 and 3? Yes. Is it true that 2 is less than -2? Nope. Is it true that 2 is greater than or equal to 3? Nope. So that's why it goes in the middle one, because that's where it fits in the domain. Okay? So why am I telling you this? Why am I going around my butt to get to my elbow? Because I'm actually showing you the biggest mistake that I see with evaluating piecewise is I see students plug it into every single function in the piecewise. You only have to plug it into one. All right? So with the piecewise, when you evaluate piecewise, you only plug into one function. Not all three, not all four, however many there are. You only plug it into one. And the one you plug it into is the domain that fits your given x. So for example, we had x equals 2. Well, the only domain that makes it true is the middle one. If you plugged in 2 for all those x's in the domains, it's not true that 2 is less than negative 2. It's not true that 2 is greater than or equal to 3, but it is true that negative 2 is less than or equal to 2, which is less than 3. Does that make sense? Kind of, sort of, maybe. Now, all you got to do once you figure that out is just what we've been doing with evaluating, which is just plugging it in to get an answer. All right, so I'm going to plug in 2 into x plus 8. So what's 2 plus 8? 10. So my answer is 10. Now, good way to check yourself if you have it in Desmos. All right, like I always say, you can always use points of intersection. So since it's intersecting the red line, I click the point. What's my y value when x is 2? 10. All right. So guys, whenever you're typing in a piecewise, you type each function individually in its own cell. And then the domains, you have to use the little squiggle bars, all right? Which I think you'd have to hit shift and then it's one of the brackets on your Chromebooks. I can't remember which one. But then you type in the inequality that they write next to it. All right? Does that make sense? Because that's another way you can figure out which function to use. All right? If the domain thing stresses you out, by all means, graph it in Desmos. Whatever x value they want you to find, set x equal to that. And then look at it and see, okay, which function does it go through? That can also help you. And you can click on the point automatically if you want to, if you don't want to plug it back in. But that's another strategy you can use. All right. Let's try another one. So x equals negative 4. Without looking at the graph, if we're looking for when x is equal to negative 4, so we're evaluating f of negative 4. Think about it carefully, all right? Don't say anything yet, but which of these three functions do you think I'm going to plug negative 4 in for x? So remember, look at the domain, see where, if you plugged in negative 4 in for these x's, see which one makes sense. Take a minute, think about it. All right, by show of fingers, 1 being the top function, 2 being the middle, 3 being the bottom. Which function do you think it's going in? So, show of fingers. If you plug in x equals negative 4 into all these domains, first off, which one would make the most sense? And then on a show of fingers, 1 being the top, 2 being the middle, 3 being the bottom. Which function do you think it's going in? It's definitely 1. Why 1? Someone who has not talked yet today. Hunter. Right. If you say these to yourself, okay, if I plug in negative 4 here, negative 4 is less than negative 2. Is that true? Yes. And then plug it into the other two just to be sure. Okay, is negative 4 both greater than negative 2, and that automatically makes it wrong, less than 3. It's not in between negative 2 and 3, so that's a no. Is negative 4 greater than or equal to 3? No. This is the only one that's true. All right. So, since x is less than negative 2, All right. Or -4 is less than -2. We're going to plug -4 into 5x minus 3. So I'm just going to replace the x. So what do I do first, PEMDAS wise? Heads up, guys. Come on. The multiplication. So what's 5 times -4? -20 minus 3, -23. Now, just to check ourselves, I'm going to go put that into Desmos. So I'm going to change this to x is equal to -4. So it should intersect the black function. Does it do that? Does it intersect the black function, which is this one right here? Yes. So that was the top function. Click on it. I, in fact, get a y value of -23? Yep. So we're right. Take a minute. Try these other two. So figure out which domain it fits in, which makes the statement true. So just say them to yourself in your head. Is -3 less than -2? Is -3 between? I keep saying -3 is +3. So say them to yourself in your head, because whichever one's true, that's the function you use. And if you want to pull up Desmos, that's fine.
She stares at me whenever she's like, Jaden, wake up. Man, I can't sleep. Everybody tries to sleep to that. It's weird. She's an owl. So what do we do? The next is D.
All right, guys, discuss with your group. Parents.
Tomorrow, Figure out which equation to go down. Greater than equal, and then you just put
What's tomorrow's street?
I don't remember. I forgot that it was even a spirit week to begin with. Oh, that's
Tomorrow's pink day.
All Wednesdays are.
I do not.
I only pick sports.
I don't think I have a single thing.
All right, let's discuss. So let's go with Abigail. Which of the three functions did you end up plugging f of 3 into? Why? Right. So since it has that equal to symbol underneath it, and 3 is equal to 3, we use the bottom function. So since 3 is technically greater than or equal to 3, because it is equal to 3, we use that function. So if I plug it in, I have 1/3 times 3 plus 7. 1/3 times 3 is 1 plus 7, that's 8. If you want to check it in Desmos, x equals 3. All right. Oh, I have it in wrong. That should be greater than, that should be greater than or equal to. If you notice, guys, so if I zoom in real quick on this, and if I click on this graph, even though it's touching both the red and the blue graph, which one is the only one with a dot? The blue. And they did that on purpose because Desmos recognizes that you said equal to on it. All right, and this one is not equal to. So 3, 8. All right. F of 0. Let's go with Reagan. So Reagan, which function did you plug 0 in for? Okay, why? Okay. Now, you may have read it backwards. So it's technically saying that 0 is less than -2. So is that true? No. All right, so which one do you think you plug it in then? So Reagan, is 0, say it again? It is the second one. Good. Because -2 is less than or equal to 0, which is less than 3. So in other words, 0 is between -2 and 3. All right. So you would plug it into the second one. So -2. All right. So we have 0 plus 8, which what is that? 8. If I check it in Desmos. All right. So if I go back and check it in Desmos, x equals 0. It only crosses the red one, so it is at 8. All right. Now, that is the first part. We just did basic evaluations. Now, let's talk about the second one. So, there are 3 linear equations. Each have different y-intercepts, specifically -3, 8, and 7, respectively. So if we look back up here, the y-intercepts of these functions is -3, 8, and 7. However, since the piecewise function is a function, there's only one y-intercept. Why do you think that is? Why would a piecewise function only have one y-intercept? Which, by the way, every function only has one y-intercept. Why is that true? Think about how the point of a y-intercept looks. What's always true about a y-intercept? The x value is what? 0. So the x value is always 0. So if there's multiple y-intercepts, is it a function? So guys, if there's multiple y-intercepts, is it a function? No, because that means you have multiple x values that are at 0. It fails the vertical line test. It fails vertical. Yeah. All right. So that's why I can only have one y-intercept, because if it doesn't, the x is repeated. All right. So 0 and some number, that's how you typically write the y-intercept. The question is, which one? Which one of these three y-intercepts is the true y-intercept? So do you guys think it's going to be -3, 8, or 7? Which one will be the true y-intercept? Oh, why would I give away the answer?
Are you playing with me?
It's 8.
Why?
It's 8.
So what do we know the x value has to equal? So x has to equal 0. Which domain does 0 fall into? We already did this one technically. It goes into the second one. So what's the y-intercept of the second one? 8. So the y-intercept is at 0, 8, because x equals 0 falls into the domain -2 is greater than or equal to x, which is greater than 3. Also, if we go back and check, all right, so if I actually go back and look at Desmos, if you look, there is in fact only one y-intercept, and it's right here, still at 8. So guys, if the whole plugging into domain thing is messing you up, by all means, just put it in Desmos. You ain't gonna hurt my feelings if you put stuff in Desmos. I expect you to do that on the EOC. All right? That's why I'm training you now, so when you get there, you'll feel more confident. Okay? Now, last problem. We're going to calculate the average rate of change of f over the interval -3, 9. Okay. Now, when you hear the word rate or phrase rate of change, what do you think? Slope. All right. So remember, we did a lot of this at the beginning of the semester. All right. So remember, slope, we're using this formula. Now, here is my suggestion when you do this. Okay, this is one where you may definitely want to use Desmos, or you can always plug and chug. So remember, the x values are the endpoints that they gave us, so 9 and 3. So in other words, those are the two pieces of the points. We just don't know what the y's are. How do I find the y's, though? So how have we been finding y's? Look at part A. Right, plugging it in. However, we still got to figure out which domain it fits in. So which domain does -3 fit into? The top, middle, or bottom? The top, because -3 is less than -2. So we're going to plug -3 into the top function. So 5 times -3 plus, was it +3 or -3? -3. 5 times -3 is -15. -3, that's -18. What about 9? So when x is equal to 9, which domain does 9 fall into? The bottom one, because 9 is greater than or equal to 3. So for 9, I'm going to plug it into 1/3 times 9 plus 7. 1/3 times 9 is the same thing as dividing 9 by 3, so that's 3 plus 7 is what? 10. So now I got my 2 points that I can plug into my formula. So remember, this could be x1, y1, x2, y2. So this is 10 minus negative 18 all over 9 minus negative 3. What happens to these minuses here? They become positive for both. So what's 10 plus 18? 28. What's 9 plus 3? 12. So if I simplify the fraction 28 over 12, what would that be? What goes into both 28 and 12? 4. So if I divide the top and the bottom by 4, what am I left with? 7 over 3. So the slope between the x value of negative 3 and the x value of 9 is 7 over 3. Now, that was a pain in the butt. Here's the easier way. So, the easier way is using Desmos. Okay? So, we know our two x values. If you wanted to, you could plug in this entire interval. All right? So, let's do that. So, in Desmos, I'm going to plug in this interval. So, negative 3 is less than or equal to x, which is less than 9. So, this interval right here is where we're finding the rate of change. Now, using the intercepts, if you've noticed, there's a lot of intercepts in this class. All right. So, using the intercepts, so here to here, you can also just do rise over run and count it on the graph. So if you count it on this graph and make sure you're paying attention to what the scale is, all right? So you would go up 28 and then over 12. And you still have to simplify that fraction, all right? But you could do it that way as well. Just go between this point to this point. Just do rise over run. That's the other way you could have done it if you forgot what the formula was, because I can guarantee you some of you will forget what the formula is. Okay, any questions on that? Okay. How are y'all feeling about piecewise so far? Are you like okay, or are you completely lost in the sauce? Be honest. Like, you're not going to hurt my feelings. All right. So, let's look at this. So, this next one is a graphing of piecewise. All right. Now, I'm not going to ask you on the test to graph, but it's still a good idea to at least know how to do it. All right. Now, the thing with piecewise is you always want to identify your endpoints, which are always the pieces on the domain. You also want to identify whether you're going to have an open or closed circle. And remember, the way you identify that is based off of the inequality symbol that's immediately next to it. All right. So for example, -2 for the top function, would there be an open or closed circle on it? So open circle goes with less than or greater than, closed circle goes with less than or equal to, greater than or equal to. So Which one would I use for -2? Closed circle. So I'm just going to do a little closed circle next to it. What about for 2 on the top function? Closed circle. We still got that equal to next to it. What about the 2 on the bottom function? That won't be open. And then what about 6? Closed. And again, I'm looking at the signs that are directly next to them. All right. So if you look at the signs that are directly next to them. Now, why is this important? It kind of gives us an idea of what the function is going to look like. So let's graph the first part of x plus 4. So I always start with a table. All right. Now, my endpoints are going to be the points on my domain. So we start with -2, we end with 2. Because remember, this domain is saying that x values have to be between -2 and 2. All right. So what's -2 plus 4? That's how we get our y values. It's 2. What's 2 plus 4? 6. And let's pick one more value. So someone pick a number between -2 and 2.
1.
Okay, 1. What's 1 plus 4? 5. All right, so just like that, we have points. So my first graph, I'm going to do -2 up to 2, and I'm going to do a big closed circle because I know it's supposed to be closed. I have 1 up to 1, 2, 3, 4, 5. I'm going to do a little bit of a smaller point just so I know that's not my endpoint. And then 2 all the way up to 6, and I'm going to do a bigger closed circle just so I know it's closed. So there's the first piece of my graph. Now, the second piece, we're going to do the exact same thing. All right, so I'm going to do another table. So my endpoints are 2 and 6, but remember, 2 has an open circle next to it, 6 has a closed. Now, if we plug in 2 for x, all right, so off to the side, I'm going to do -3/2 times 2 over 1. So what's -3 times 2? -6. What's 2 times 1? 2. What's -6 divided by 2? -3. And then we add 9. So it's -3 plus 9. 6. I'm going to do the same thing for 6. Plug it in for x. So I have -3 over 2 times 6 over 1. What's -3 times 6? -18. 2 times 1 is 2. What's -18 divided by 2? -9. Add 9 to it. What's -9 plus 9? 0. Now we're going to pick one more number. All right. I recommend an even number. So I'll pick 4. So remember, you want to be between 2 and 6. Whatever number you pick, as long as it falls within that domain, that's a reasonable number to pick. Now, why I said even number? Because that'll get rid of the fraction. All right. And how do I know that? That's just from years of experience. All right. Now, if you picked like 1 or 3, that's fine, or 5. You would just have to deal with graphing a fraction. That's the only downside of it. All right. So, -3 times 4 over 1. So what's -3 times 4? 2 times 1? -12 divided by 2? Plus 9. 3. So I got an open circle on 2, 6. So even though there's already a closed circle there, I'm just going to draw an open one around it. And then I'm going to do 4, 3. and then 6, 0 with a bigger closed circle. So my graph looks like my graph looks like this. Now, we can't just leave that open circle like it is. So here's kind of the rule of thumb. Just like if you were playing rock, paper, scissors, how rock beats scissors, scissors beats paper, paper beats rock. Closed circle beats open circle. So if you have a closed circle and an open circle on the exact same point, you can remove the open circle and leave it as closed. All right, so closed circle always beats open. But that's only when it's on the exact same spot. Like, I mean, same X, same Y. All right. Now, what do you think the range of my function is? So we're talking X or Y values first off. Y values. So what's the lowest Y value that I have on here? 0. And where does it go to? What's the highest Y value? 6. Now, do I put parentheses or brackets around it? Brackets. Because remember, closed circles, you use brackets. It's defined. Now, is the graph continuous or discontinuous? So what that means is, if we ran our pencil from left to right along where our graph is, does it break? Are there any holes? And by holes, I mean open circles. So are there any gaps in the graph? Nope. So it's continuous. Any questions on piecewise functions? All right, so you all got a solid 20 minutes until the end of class. You should be able to finish the rest of that delta math. Yes, ma'am. Yeah. Put your name on the board. She already asked. So I expect everyone to get their Chromebooks out. And be working on that delta math.